So now here's an example of Rolle's theorem. We are going to verify that the function f of x equals x times x minus 6 quantity squared satisfies the three hypotheses of Rolle's theorem on the closed interval from 0 to 6. Then we're going to find the value of c that is guaranteed by Rolle's theorem. So the three hypotheses of Rolle's theorem for us to verify are that it is continuous on the closed interval. So first, we're going to point out what kind of function f is. So f is a polynomial function, and by a theorem from the section on continuity, we can say thus, f is continuous on its domain. Which is all real numbers. Therefore, we can draw a conclusion that f is definitely continuous on any closed interval within all real numbers. The one that we're looking for specifically in this problem is the closed interval from 0 to 6. Next, we need to show that f is differentiable on the open interval from 0 to 6. The way that we can do so is by actually finding the first derivative of f and then verifying that the first derivative is continuous. So I am about to take the derivative, d over dx, of x times x minus 6 quantity squared. Now I could expand this polynomial, or I could simply go with the product rule. I believe I'm going to go with the product rule. Eventually we're going to want to factor this for the value of c guaranteed by Rolle's theorem anyway. So we'll do the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. Now for the derivative that's left over for the first part here, we can apply the chain rule and call that 2 times x minus 6 to the first power times the derivative of the inside. Derivative of the inside, thankfully, is just 1. Then for the last derivative here at the end, derivative of x with respect to x will simply be 1. Now, in its current form, we have enough information to conclude what kind of function this is. So we can point out f prime is a polynomial function. Thus, f prime is continuous on its domain. Domain, there we go. Which is all real numbers. Now, we only need that it's differentiable, therefore f is differentiable on the open interval from 0 to 6. And finally, we need to verify that f of 0 is equal to f of 6. That is the third hypothesis of Rolle's theorem. Now, we are going back to the original function back up here to plug these values in. So plugging in x equals 0 is going to be 0 times 0 minus 6 quantity squared. Well, 0 times anything will be 0, so we're all set there. Then for f of 6, that'll be 6 times 6 minus 6 quantity squared, and you'll notice that what we get inside the parentheses is going to wind up being 0. Therefore, f of 0 is equal to f of 6. Now, that verifies the three hypotheses of Rolle's theorem. Next up is to actually find c with f prime of c being equal to 0. Now, since we already took a derivative, I'm going to go ahead and come back to this derivative and perform a little bit more algebra, but because it's c, I'm going to replace all of my x's with c's. So we'll call this 2c times c minus 6 plus c minus 6 quantity squared. We're going to set that equal to 0. Now, I do want to point out that there is a common factor of c minus 6 that you can pull out from these two terms, c minus 6 times. If we factor that from the first term here, we're going to get 2c. And if we factor it from the second term, then we'll still have a c minus 6 left over. This is still equal to 0. Combining like terms inside my brackets here, that's going to be c minus 6 and 3c minus 6. I notice that there's a common factor that I can pull out of that set of parentheses, and that would be 3. We'll still have c minus 6 times c minus 2. So if we were solving this over all real numbers, we would arrive at the following conclusion. That would be c is equal to 2 or c is equal to 6. However, the statement of Rolle's theorem, the conclusion of Rolle's theorem, is that c has to be in the open interval from 0 to 6. Therefore, c is not allowed to be equal to any of its endpoints. Rather, it is a point on the interior of the interval. So it can't be an endpoint, so our final answer for this one is c equals 2.